We have this theory of the world that explains almost all of reality. We call it the core theory, something that has worked so well that it has to have been on the right track. This core theory has certain missing pieces, some things that it doesn't have, some things that it doesn't account for, and certain cracks we don't know how to fill. Yeah, it doesn't look that good, but this is a picture that works really well. We've come so close to the fundamental nature of reality that we might just be a breakthrough to away from a theory that truly explains everything. The problem is, we are stuck for a long time with the same nagging question. How do we go beyond this core theory? If you ever go deep into physics circles, you'll come across this outburst that particle physics is dead. Particle physics is this thing that tries to explain all of reality by breaking things down to its most fundamental constituents and then using those to explain the larger universe. Yes, this is the good old reductionist paradigm, from the idea of an atom, a curiously indivisible entity, to actually finding something that seemed like an atom, only to discover that it wasn't really indivisible at all. And since then we've discovered substructure after substructure, taking us right now to something that culminates to the standard model of particle physics. A framework that not only goes the deepest into reality, but also is stupidly accurate. There are certain results coming out of this theory, and when you match them against observations, you get results that match up to 10 to 13 places. That's absurd for any sciences, yet alone particle physics. And that makes one thing very clear. The standard model is a very good description of reality. But we also know with complete certainty that's not all that there is. For one, it doesn't have gravity. For gravity, we have the general relativity, so a classical theory that knows not about the quantum world, while the standard model is this theory of the quantum world that don't know how to talk about gravity unless encountering absurdities. Where's the issue? The issue is we have this model of the world that works so well and yet can't be fundamentally true. And we don't know where to go. It's like being stranded on a spaceship with no map, no coordinates, nothing. And the spaceship is malfunctioning. By malfunction, I mean the standard model has some really glaring issues that hit you on your face, saying there's something wrong. In this video, we'll talk about how we ended up here, why things aren't working, what might lie ahead, and how things might actually turn around. Keep watching. Okay. Imagine you are in the 1960s. The physics world is confused. Confused because there's so many particles that we found and we don't know what to do with them. The key aspect of discovering a new particle has largely been smashing particles at higher and higher energies. At first, they were cosmic rays, so particles coming from deep space at near light speeds and hitting the atmosphere. The collision leads to a plethora of charged particles raining down on the surface, where they can be detected by detectors. But once we were able to develop our own particle smashers, the number of particles being discovered skyrocketed. There was a flurry of new particles being discovered. Hundreds of seemingly new particles, all with their own different properties, all begging for an explanation for their place in this world. It was a mess. The situation was hilariously bad. While collecting his 1955 Nobel Prize, Willis Lamb said, "The finder of a new particle used to be rewarded by a Nobel Prize, but such a discovery now ought to be punished by a $10,000 fine. This is not adjusted for inflation. That is to be done by yourself." Hilarious. It's understandable though. It is one thing to find a particle that you were expecting, but completely another to be bombarded for an explanation of why on earth are there so many different elementary particles. This is a very different world to where we are right now. Right now, we are looking for new particles, any one of them, with any hints whatsoever to what might lie ahead, and we will take it. So what happened? Something clearly did, because I showed you that image, right? There doesn't seem to be hundreds of particles here. I mean, there are different ways you could count how many particles are here, but most people would say there are not hundreds of them here. So what happened? Yes, something did happen. A way of looking at this particle mess that simplified everything. Quarks. So again, there was this particle mess. Physicists Murray Gell-Mann and Joel Zweig came up with this way of arranging particles based on properties like mass or something as strange as strangeness, literally. There was this particular arrangement called the Eightfold Way, and many others like it, and a pattern emerged. They came up with this idea that all these different particles that we were seeing aren't all that elementary, rather they're themselves composed of tinier entities, quarks. With the particles that were present back then, they only needed 3 quarks, the up and a down quark that make up the atomic nuclei, and a strange quark. Get it? Strangeness. Now what would you do? There is in front of you this idea that solves all your particle mess. Would you take this idea further and be like, you know what, this is real, quarks are real? Or would you be more inclined to think of this just as a toolkit, a way of simplifying bookkeeping that works but isn't inherently how the world works? Most physicists back then thought that quarks are just a useful fiction. Murray Gell-Mann himself ends his 1964 paper saying, a search for stable quarks of charge minus a third or positive 2/3 at the highest energy accelerators would help us to reassure the non-existence of these quarks. What he's suggesting is to look for particles with fractional charges, and not finding them would tell us that they don't really exist. The experiments thereafter did not find particles with fractional charges, but something else did happen that proved that quarks are real. Deep inelastic scattering. It is this process in which you throw electrons at protons or neutrons, and the way they bounce off holds information to what constitutes them, or if anything constitutes them. And the scattering was as if these were really bouncing off of certain point-like objects inside protons. With time, it became clearer that this something is not anything else but just quarks. Fast forward and we found more quarks, more elementary particles, and ended up with this, the Standard Model that we know. There's one thing worth pointing out here. If you see the Standard Model, you'll see that these particles are really present in generations. Like at a roughly same energy scale, you'll get the up and the down quark and the electron and electron neutrino. Great, but if you raise the energy a little bit and get to a higher energy level, you'll again end up with a similar set of 4 particles. The strange and the charm quark, but also with them the muon and the muon neutrino, where the muon is nothing but a heavier cousin of the electron. It has the same electronic charge, but is like 200 times more massive, so a higher energy scale. If you go to even higher energies, you'll end up with another generation of particles, the top and the bottom quark, but along with them the tau and the tau neutrino, where again tau is nothing but 20 times more heavier than muon, same electronic charge. And that's about it. There seems to be these 3 generations of particles, but no more. Why 3? Well, it is one of these questions that we can ponder about, but we really have no clue why that is, or if there is a reason. And that is not a reason that there is no reason. That's bad. The other thing about the Standard Model is that even though it works really well, it still requires a lot of parameters to be set from experimental data. So you go out in the real world, you measure the values of these different parameters and you put them back on the theory, and that's the only way the theory is of any use. There are as many as 19 such parameters. The theory by design says nothing about why they have the values that they do. And it's not that big of a criticism because every other theory also does that. It's just that if we're looking for something to describe reality so deeply, we'll like this number to be a lot less, if any. Added to this, there's always the anthropic argument that we would ever see ourselves be in a universe that allows us to exist, have any significantly different values of these parameters, and we wouldn't be there to observe the different values. Works really well in a multiverse where each of the different universes have their own different values of these parameters. And we don't know if the multiverse is real, that's always there. So far these are really just nitpickings, but there are some actual cracks as well. For instance, in the Standard Model, neutrinos are supposed to be massless, but they do have mass, and we know that they do have mass. I've got a video. Or the fact that the universe has all of this dark stuff, and Standard Model doesn't account for that. So dark matter, dark energy, Standard Model doesn't know about them. Or the big one, the world has gravity, Standard Model doesn't have gravity. It can't be true. Like, that's trivial. These were the big ones, but going a bit further, we encounter stuff that just doesn't make any sense. For instance, the hierarchy problem. There are many different ways to talk about the hierarchy problem. One of them is the Higgs boson's mass. The way the Higgs boson gets its mass, we expect it to have contributions up till the Planck scale. And we would expect all these different contributions to blow up the mass of the Higgs. And yet, when we measure the mass of the Higgs boson, it's a meager amount. It's a very unnatural cancellation. It seems as if the mass is somehow finely tuned or something. And that doesn't make sense. It doesn't feel right. Ideas like supersymmetry hypothesize a superpartner particles to each of the particles of the Sand model with the opposite contributions, giving rise to the perfect cancellation. The problem with supersymmetry is that we did not find any superpartner particle. And this connects to the fact that the LHC wasn't just supposed to find the Higgs boson. We also expected to give rise to some insights, some new ideas, new particles, new interactions that might pave way for physics beyond the Sand model. That didn't seem to have happened. I mean, there have been some exciting progress, but not as much as people were hoping for. Which takes us to the present. We have a really great idea that works really well, but can't be fundamentally true. There have been new ideas and modifications, but we don't know which ones are rooted to reality. Particle physics is hard. You work on an idea not knowing whether or not it's actually real or it's just pure mathematical fascination. We have so many people around here that are so deeply interested in high energy physics, and they should, because this is something that takes us the closest to the universe. And yet, we're here all around. Particle physics isn't going anywhere. People are switching their fields and working on ideas that have more impact, because particle physics has just reached a level of abstraction from where, even if you did have the right idea and the right insights, there are so many other ideas that it'll still go nowhere until there are reasons to believe that your idea was the right one. And so, we are stuck. This kind of reminds us of Thomas Kuhn's ideas about how science progresses. Generally, there is incremental progress, small steps within a paradigm, until you're met with anomalies, which eventually lead to a crisis. And then a paradigm shift occurs, a revolutionary leap in understanding, and the incremental progress restarts. Particle physics isn't dead, but to say that nothing's wrong is also not true either. Particle physics is in need of its breakthrough. One result, one finding, and the entire field may re-emerge with more power. With AI having set its foot on the fundamental sciences, it's not hard to believe that the next breakthrough might come from AI. Or maybe not. To end, we've reached a point from where we're not really as far in terms of the number of breakthroughs from a theory of everything. The holy grail of physics, something people have spent their entire lives on. Who said it's gonna be easy? Thanks for watching.